Welcome everybody to lesson 1 of unit 4. We're talking about trigonometry in the next couple of units. So let's start off lesson 1 by talking about radians and degrees. First of all, we're going to be working a lot with something called a unit circle. And before we even get to that, we've got to start working with radians and degrees. What a radian is, it's the measure of a central angle theta that intercepts an arc equal in length to the radius. Okay, and we'll show you what a picture of that is in a moment. But we need to know a couple of things real quick. We have an angle right here, and we have two parts of an angle. We have the initial side, which will always be on the positive x-axis. That's where it will always be located. And as we have a positive degree or radian measure, our angle will open counterclockwise. And wherever our angle ends, we would call that side the terminal side. Okay, so your initial side is where it starts, always on the positive x. We move and we land on our terminal side. Okay, so let's see what's going to happen here. Okay, with the radians, first of all, on a coordinate plane, 1 pi is going to be equal to half of a circle, right? We're going to go from one side to the other. That's worth pi. So that would mean then that if we were to travel all the way around, from one side all the way over, that would be worth 2 pi. And then we have smaller increments, right? If we were to go only to the y-axis, starting here and then ending here, that's halfway to pi, so that would be 1/2 pi, or pi over 2. And then we have some other ones that we can look at, right? We could look at this particular area right here, or that angle, which would be a 1/4 pi, right? It's halfway between 0 and 1/2 pi, so that would be a 1/4 pi, or pi over 4. So there's all sorts of different things we can look at. We're also going to be looking at pi over 3, 2 pi over 3, and very similar to that. Okay, but that's how we would measure these things. And the two that are extremely important right now for us are pi and 2 pi, because we can get a lot of these smaller angles just from knowing these two. Okay, so we're going to talk about some things now that are called coterminal angles. Remember, we were talking about the terminal side before. Right? Coterminal angles are angles that have the same initial and terminal sides. Okay, that's great and everything, but what's really interesting about coterminal angles is that we can have different measures that still have the same terminal side. And that's what we're going to see right here. If we want to find a coterminal angle with a different angle measure, we're going to either add or subtract a full circle, which would be 2 pi if we're working in radians, or if we're working in degrees, 360. Okay? So let's look at some examples of this. We want to find a positive and negative coterminal angle to 93 degrees. So if we want a positive, we're going to add 360 to 90. So 93 rather. So 93 plus 360, that gives us 453 degrees. So this angle here and this angle here would share a terminal side. If we want a negative, we would take 93 and subtract 360 degrees. And that would give us negative 267 degrees. So all three of these angles, they're all landing in the same spot. This one we would have to go around a full extra time. This one we'd be going in clockwise direction. Okay? Here we have radians, right? 3 pi over 5. So now we want to be adding 2 pi. So we have 3 pi over 5, and we're going to add 2 pi. Normally 2 pi is over 1. And in order for us to add these, we need to have common denominators. So I'm going to multiply this whole thing by 5 over 5. That'll give me the common denominator that I need. And when we add, we get 13 pi over 5. That's our positive coterminal. If we want negative, we're going to be subtracting 2 pi over 1, which we already knew was going to be 10 pi. So 3 pi over 5 minus 10 pi over 5, that's negative 7 pi over 5. So all three of these angles all in the same place. So there's two problems right here for you to try out on your own. Pause the video and resume when you're ready to check your solutions. Alright, let's see how you did. If you want a positive coterminal angle, we're going to add 360, and you should have come up with 496 degrees. If we want a negative, we're going to take 136 and subtract 360, and we come up with negative 224 degrees. Then we have radians, right? 2 pi over 7. 2 pi over 7 plus 2 pi over 1. I have to multiply this whole thing by 7 over 7, so that gives us 2 pi over 7 plus 14 pi over 7. 2 and 14 is 16 pi over 7. And likewise, we know that this is equivalent to 2 pi, right? 14 pi over 7. So I'm just going to subtract that now. Alright, 2 minus 14 is negative 12 pi over 7. How'd you do with those? Hopefully you did okay. Finding coterminal angles. Okay. Now we're going to talk about complementary and supplementary. We've talked about these in geometry, but we still need to be talking about them here in trig. Okay. Complementary is two positive angles that add to 90 degrees, or now with radians, it would be equal to pi over 2. Supplementary, very similar, two positive angles that add to 180 degrees, or in radians that'd be pi. Right? So if we want to find a complement or supplement, we're going to be adding what they give us plus some sort of variable that we're going to be solving for, and set it equal to either 90 pi over 2 if we're working in radians, or if we're finding a supplement, we'll make it equal to 180, or pi if we're in radians. Pretty simple. Okay, so let's see. I know for a complement I would be starting at 90, and if I get rid of 66, it'll leave me with what complement angle I need, which is 24 degrees. So the complement to 66 is 24. If I want supplement, we know that that's 180. I'm going to get rid of the 66 to find my missing angle of 114 degrees. So here we have a complement and a supplement. Here now we're working in radians. If I want a complement, we know that that's pi over 2, and I'm going to subtract pi over 3. These don't have common denominators, so we're going to have to multiply by 3 on bottom and top here, and by 2 on bottom and top here. That will give us a common denominator of 6. Right? So what we have is 3 pi over 6 minus 2 pi over 6. 3 minus 2 is pi all over 6. Okay, not too bad, right? That's complement. Supplement, we need to be working from pi. So I'm going to take pi, which we would assume to be over 1, and I'm going to subtract pi over 3. Okay, I need to multiply by 3 over 3 here. So that gives me 3 pi over 3 minus pi over 3, which is 2 pi over 3. So now we have a complement which would add to pi over 2 or 90, and we have a supplement which would add to pi, or 180. Okay, so there's two right here for you to try. You're finding the complement and supplement. I'm going to leave the work from above so you can still see it if you need something to refer to. Alright. Hopefully you paused the video just now to try these out. Let's see how you did. We want to take 90 for complement and subtract what we already know, and we're going to end up getting 47 degrees for a complement. For a supplement, we take 180 and get rid of what we already have, and that leaves us with 137 degrees for a supplement. Those ones are pretty easy. Radian's a little more work, right? We need pi over 2 for complement, and we're going to subtract 2 pi over 5. Hopefully you recognize we need to multiply by 5 over 5 and 2 over 2. So we've got 5 pi over 10 minus 4 pi over 10, and that gives us just pi over 10. If we want supplement, we take pi, I'm going to put it over 1, and we're going to subtract 2 pi over 5. Oops, 5. We need to multiply this whole thing by 5 over 5. This doesn't have to change, so we've got 5 pi over 5 minus 2 pi over 5, which leaves us with 3 pi over 5. How'd you do with those? Good? I hope, right? These ones not too bad. Just simple subtraction. This one, yeah, we have some fractions we have to work with, but no big deal. We've been working with fractions for a while. Okay, now we're going to work with converting radians and degrees. Okay, take a second to write down these conversions. These are going to help us out in the next few. If we want to start in degrees, or if they give us degrees and we want to change to radians, here's our formula. We're going to take whatever angle they gave us in degrees and we're going to multiply by pi over 180. If we're working with radians and we want to convert to degrees, we're going to multiply our angle by 180 over pi. Now what's nice is that usually radians involve pi, right? The actual pi symbol. And we notice the actual pi symbol here. So what we're going to see when we do some of these problems down here is that when we convert from radians to degrees, the pi's will actually cancel out, which is how I remember which formula is which. I want pi on bottom because usually in radians pi's on top and they'll eliminate. Okay, so if you need some sort of memory technique, that's what I usually do. Okay, so we want to convert 100 degrees into radians. So we're going to take 100 and we're going to multiply it by pi over 180. I'm going to put 100 over 1 as well. Okay, now you have some options, right? You can start dividing by common factors, right? So if I divide 100 by 20, I'm left with 5. If I divide 180 by 20, I'm left with 9. And now we can do our multiplication straight across. 5 pi over 9. So 100 degrees is the same as 5 pi over 9. If we have 225 degrees, 225 over 1 times pi over 180. I'm noticing that these are both divisible by 45. If I divide this by 45, we get 5. When we divide 180 by 45, we get 4. Multiplying straight across, 5 pi over 4. The next two problems, they ask us to convert to degrees. Notice how we're starting in radians. We already have the pi symbol, as I mentioned earlier. So 7 pi over 3 times 180 over pi. And as I mentioned, I remember that because look what happens to my pi's. They eliminate each other. Okay, and now we can start simplifying, right? I know that 3 and 180, those can reduce. And now I'm just going to multiply. I have 7 times 60, which is 420 degrees. Our next example, 11 pi over 6. We're going to multiply by 180 over pi. First, our pi's eliminate. 6 and 180, those are both divisible by 6, leaving us here with 30. And then we multiply 11 times 30, which gives us 330 degrees. So there are two for you to try. This is convert into radians. This convert into degrees. Make sure that you use the correct formulas for that. Pause this video and try it out, and then resume when you're ready to check. Alright, let's see how you did with this. We're multiplying 300 over 1 times pi over 180. What we want to do is think about what common factors we have. If I divide 300 by 60, we're going to be left with 5. And if we divide 180 by 60, we're left with 3. Now I multiply straight across. 5 times pi is 5 pi. And then 1 times 3 is 3. So 5 pi over 3 is the same as 300 degrees. We want to convert 4 pi over 3 to degrees. We're going to multiply by 180 over pi. Our pi's eliminate. 3 and 180 will reduce. So now I have 4 times 60, which is 240 degrees. And converting radians to degrees is not really that difficult. Make sure you take your time with them. Now, we've been doing all that for some setup for some more stuff. What stuff am I talking about? It's something called radian arc length. Okay, we've talked about arc lengths in geometry. An arc is just a piece of a circle, right? So we want to figure out how long an arc might possibly be. So this is the formula for it. Arc length, which we're going to abbreviate to S. I have no clue why arc length is S. I'm sure someone on the interwebs somewhere can tell us, but that's our variable. It's going to be equal to the radius times the central angle theta in radians, which makes sense because this is radian arc length. So here's your formula. Arc length equals radius times theta. So what do we have to do? We have to take whatever they give us and convert it into radians and then multiply by the radius. Pretty simple. Okay? So this problem right here says find the length of an arc with a central angle of 270 degrees with a radius of 5 centimeters. This is not in radians. So it's a good thing that I showed you how to convert first. So we're going to take 270 over 1 and we're going to multiply by pi over 180. That can reduce. These are both divisible by 90. So 270 divided by 90 is 3. 180 divided by 90 is 2. We multiply straight across. And we've converted now to 3 pi over 2 for our central angle, right? Theta. Our radius, we don't have to do anything to. They told us it was 5. So when we want to find arc length, we have S equals 3 pi over 2 times 5, which I'm going to put over 1. And I can now multiply straight across. 3 times 5 is 15 pi all over 2. Now, we want to know how long that is in centimeters. So we have to type that into a calculator. If you have Desmos, which is what I'm using for trig in this particular program, okay, Desmos works really well. You can use a TI calculator, usually has the pi function, all sorts of calculators, okay. So we're going to type in 15 pi over 2. Make sure that it's set in radian mode this time. okay, 15 pi over 2, and it's going to spit out 23.56 centimeters. So we have one more for you to try right here. Okay, I'm going to leave the problem above as an example, so you can pause the video and resume it when you're ready to check your solutions. Alright, let's see. We want to find the length of an arc with a central angle of 35 degrees and a radius of 8 inches. 35 degrees is no good. We've got to convert. So I'm going to do 35 over 1 times pi over 180. When I reduce these, 35 is divisible by 5 and we get 7. 180 divided by 5 is 36. So our angle theta is going to be 7 pi over 36. If we want the arc length now, we know the radius is 8. We don't have to do anything to that. So we're just going to multiply 8, and I'm going to put over 1, times 7 pi over 36. We can multiply straight across at this point if we'd like to, because we're going to handle everything else in the calculator. So 56 pi over 36, punch that into your calculator, and it's going to come out to be approximately 4.89 inches. Be careful with your rounding. Okay, this would have actually said 4.886, and that 6 would have told this 8 to round up. Okay. Not done quite yet. I know it's been 22 minutes already, but I've got one more little bit of stuff to look at. Linear and angular speed. These are actually kind of cool because we see problems like this all over the place, especially now with the green movement in electricity and power, right? We see wind turbines, we see things like fidget spinners that kids are playing with all the time instead of listening to class instruction, right? All sorts of stuff that spins. So this is really pretty cool to work with. Okay? We have two different types of speeds. We have linear speed, which is how fast an object travels along an arc, and linear speed will be arc length, which we just calculated a minute ago to be s, divided by time. Okay? Then we have angular speed, which is how fast the central angle is growing. So imagine that you have your terminal side is moving and your angle is growing at a certain rate. Okay, so angular speed will be whatever our central angle is divided by time. Okay, and we're going to be working in radians for all of this. So let's look at an example. And I'll leave these up here for us to reference too. Okay, it says an airplane propeller blade is 13 feet long and rotates at a rate of 15,000 revolutions per minute. We want to find the linear and angular speeds of the propeller. By the way, anybody who flies planes, I don't know if those are correct numbers or not. I kind of made them up a little bit, so this might not be the most realistic numbers, but it's going to work for us anyways. Okay, so linear speed, we'll start with that. We know linear speed is going to be angular, or arc length rather, divided by time. And we said that arc length is going to be theta times radius over time. Now, here's the deal. We already know our radius is 13 because they told us that right here. What we need to know is what theta is. Now let's think about it. It said 1,500 or 15,000 revolutions per minute. One revolution is worth 2 pi. And I have 15,000 of those per minute. So I'm going to multiply by 15,000. And I'm going to keep my units of time in minutes, right? Because we're talking about per minutes anyways. So right here we'll be able to multiply. And we're going to get 30,000 pi for our theta over the course of a minute. Okay, so over the course of a minute, the angle has opened up to 30,000 pi. That's what's happening here. So now we can start substituting in. We have 30,000 pi times 13. And because our unit of measure is still going to be minutes, we only have 1 minute that all of this is happening. So it's going to be over 1. And we can type in this directly into a calculator, and it's going to spit out 1,225,221 feet per minute. Alright, so what is actually happening here? Here's our airplane propeller. Right, this is looking at the front of the airplane. What's happening is the tip of this 13-foot long blade is spinning around and around, right? Just keeps on going around and around. And it's going around that many times per minute. Okay, so what's happening is if we were to take this circle that we just drew, all of 15,000 of them, and we were to stretch them out and measure it, it would be that long. Okay, that's very long. Now we want to work with angular speed. Okay, angular speed, we know, is going to be theta over time. Well, we were lucky because we already found theta to be 30,000 pi. So all we're going to do is put 30,000 pi on top. We're still talking about minutes, so it's going to be 1 minute underneath. So our answer for angular velocity, angular speed is going to be 30,000 pi radians per minute. So what's happening here? Well, let's go back to our little picture. This angle that's being formed here, okay, basically it starts with nothing, right? It starts at a 0 angle, and then it's going to open, and it's going to continue to open over the course of that minute to 30,000 pi's. Remember, pi is from one side of the circle to another, right? So it's hitting from one side and then going to another and another, and it's doing that 30,000 times over the course of a minute. That's what's happening visually. So I have a problem for you to try. You're going to pause the video and resume when you're ready to check your solutions. Alright, let's check it out. Fidget spinners. Everybody loves them, right? A fidget spinner has a radius of 4 centimeters. You are able to spin it at a rate of 400 rotations per minute. Again, I don't really know if that's possible or not. I just kind of made up some numbers, but whatevs, right? So here we go. We want to find linear and angular speed. We know our radius, they told us, is 4 centimeters. And we know that we're working in minutes per minute. So we're going to take, for theta, we're going to take 2 pi, which would be a revolution, right, or 1 full rotation, and we're going to multiply it by 400, because that's how many times it happens in that minute. And we get 800 pi. Now we can start filling it into our linear speed equation, which is radius times theta over time, which is still just 1 minute. And we can type that right into a calculator. 4 times 800 pi, and you're going to get 10,053 centimeters per minute. That's how far a little point on your fidget spinner would travel in the course of a minute if you were able to hit it to 400 rotations per minute. That's assuming, by the way, that it's not going to slow down, right? We're working in the perfect world. Okay. Next, we have angular speed. Angular speed is theta over time. Our theta we already calculated to be 800 pi. Time is still going to be 1 minute, so here's your answer for angular speed is 800 pi radians per minute. That's it for this lesson. that was a lot of stuff. A full 30 minutes worth of notes. Hopefully, none of this went too far above anybody's head. If you have any questions, just bring them with you to class, and I'd be more than happy to talk about them there, or you can leave some comments in the comment section. Until next time.